This is a picture of a neon sign. And this reddish-orange color is what you get when you put neon gas in a tube and pass electricity through it. It will glow. And when you turn the electricity off, it stops glowing. And you turn the electricity back on, and it starts glowing again. So when you put neon in a glass tube, it'll do that. You can do that with other elements too. If you put mercury in a glass tube and pass electricity through it, you'll get a blue light. If you use hydrogen, you'll get a pink light. Why do they give off different colors? That was a question. If we take light from the hydrogen lamp, that pink light, and pass it through a slit and through a prism and separate it, instead of seeing a continuous rainbow, we see 4 lines. And each of those lines is a different color. The colors line up with the colors that would be there if it was a regular rainbow. But we only get these 4 skinny little lines. And that was something that was observed, and that was really the impetus for the development of the Bohr model of the atom. So here on the top, these are called emission spectrum, that's singular, or emission spectra is plural. Here's a white light emission spectrum. So if you took light from the sun or from an incandescent light bulb, this is what you'd see when you pass the light through a prism. This is what we expect. From a hydrogen lamp, you get 4 discrete lines. And see how the color of this one lines up and matches the color here? And this color matches because they're being separated by their wavelength. And so the hydrogen light is emitting light with only 4 different wavelengths within the visible spectrum. If we do helium, we get more lines. These lines are similar in color, but they're not exactly the same wavelength. And now we've got this new one in the yellow, and these blue ones are different than the ones that hydrogen had. Neon gives a whole bunch of lines, but again, it's specific lines. It's not a continuous spectrum. This one's continuous. There is every wavelength of light. This is non-continuous. There are only specific wavelengths of light. And that was a big deal. Scientists recognized, this is weird. What's going on? Why? Why is it doing this? And so this is what they came up with. Niels Bohr developed a simple model to explain why does the light from a hydrogen lamp give us these lines and what do they mean. So the Bohr model is a lot like a model of the solar system. And we now know that it's not true, but it's still helpful to look at. Here in the center is the nucleus. What's in the nucleus? Protons and neutrons, right? We've talked about that. And we said the electrons were outside of the nucleus, but we didn't say what they were doing. Well, in the Bohr model, what they're doing is they're behaving very nicely, and they're traveling in circular orbits around the nucleus, just like the planets go around the sun. And that reminds me of a class I had a few semesters ago, and I was talking about that, and a guy in the back raised his hand, and he says, how much do telescopes cost? And I'm like, I guess, solar system got him thinking about telescopes. Yeah. I was just so taken aback, I just didn't even, I tried to give an estimate on telescopes. I just couldn't even respond. So weird. I'll never forget that guy. He also came in once and he'd wiped out on his skateboard and needed Band-Aids. Oh, it's fun. It's just fun. Okay, so solar system, orbits. So the electrons have these orbits, and he numbered them 1, 2, 3, 4, 5, just nice and in order, nothing crazy like that. Each of these orbits has a specific distance from the nucleus and a specific energy. And the farther away from the nucleus you go, the higher the energy of that orbit. And if you've done anything with physics and learned about how satellites orbit the Earth, You know that you can establish orbit at different altitudes, but the speed has to be right, and there's all these factors. And so it's a little bit like that. But each of those orbits has a specific level. So you can be in level 1, orbit 1, they're like rungs on a ladder. Or you can be on level 2, or level 3 or 4 or 5 or 6. You can't stand between level 1 and level 2 on a ladder, can you? There's nothing to stand on. A ladder is quantized. There are discrete levels, and you can't be in between. That is in contrast to something that is continuous. So a ramp is continuous. You can be at this level, you could move down a smidge, you could be anywhere along that ramp. Your distance above the ground could be anything from here to 0. A ladder or a set of stairs, I don't know, this morning the stairs had 3 steps, now they've got 4. Stairs are quantized. You can stand on the first step or the second step or the third or the fourth. You can't stand in between. You can only be a certain distance above the ground and not in between. We have examples of quantized and continuous things in real life. Our monetary system is quantized. There are pennies and nickels and dimes, and the bills, there's 1s, 2s, 5s, 10s, 20s. You can't have an $18.31 bill. It just doesn't exist, right? It's quantized. Grades in school, you can be in first grade, you can be in second grade. You can't be in between. You're in one or the other. Instruments, a piano is quantized. You can hit C or C sharp. You can't make a note in between. On something like a violin, you can make notes, sounds that are between notes on the piano. And so it can get really kind of off. I played the violin in school when I was young. It can sound really awful. And part of that is because you can play all these notes that are in between notes, so you can really be off. You can't do that on a piano or a guitar. A guitar has frets, and when you press the string, it stops at the fret no matter where your finger is. And so you get the note that you were aiming for. Quantized. So the orbits for the electrons are quantized. So the electron can be in the first orbit, or the second, or the third, or the fourth, or the fifth. It cannot be in between. And what's really hard to get your mind around is that it can move from one orbit to the next without being in between. That's called a quantum leap, where you go from one place to another without being in between them. And the Bohr model does not really explain how that happens, but quantum mechanics does. So what happens to those electrons in the hydrogen atom when it absorbs this electrical energy? Well, if we bring in energy, this electron gets excited. It can absorb some of that energy and go up to a higher energy level. It's not going to stay up there, though, because that's unstable. And eventually it will relax down to a lower level. It could go down one level, it could go all the way down to the first level. It doesn't have to go one step at a time. But what happens to the energy? The energy has to go somewhere. Energy isn't created or destroyed. So electrical energy came in and excited this electron, jumped it up to a higher energy level, and then it relaxed down. That energy gets released. And some of that energy is released as visible light. If the wavelength is between 750 and 400 nanometers, it comes out as a light that we can see. And that's what we're seeing when we see that pink glow from the hydrogen lamp. The energy, the light that is emitted here is a photon. a quantum, a packet of light, a piece of energy, a discrete piece. You get one quantum, one photon for every electron that relaxes. I think of electrons as being a little bit like my sons, especially the teenage ones. Their ground state is generally horizontal. And now that my third one is 13, he's exhibiting this behavior as well. Where's Tommy? Well, you usually find him in his bed, either sleeping or listening to music or watching a movie on his iPod, right? He's resting, okay? And then he'll have these bursts of energy and he'll get up and he'll go to football practice or he'll go to basketball practice or he'll go out and shoot baskets. But you can't sustain that forever, and eventually he comes back and it's horizontal again. Maybe this time on the couch watching television. So the electrons do this. They'll get some energy, and they'll go up to this higher level, but they can't stay up there, and they come back down. When they come back down, they give off light. The energy of this photon corresponds to the difference in energy between these two levels. So here's a different illustration. So if the electron in a hydrogen atom goes from level 3 down to level 2, the energy that is given off as light corresponds to a wavelength of 657 nanometers, which is red. The blue-green line is from level 4 down to level 2, and that violet line is from level 5 down to level 2. These wavelengths can be measured. From the wavelength, we can calculate the energy. So Bohr was able to do all these awesome calculations and calculate the energies of the orbits of the electrons in the hydrogen atom. And it was, wow, it was just amazing. So he predicted the lines in the hydrogen emission spectrum. The problem was it only worked for hydrogen. And if you try to use helium, which has 2 electrons, it doesn't work. Well, a model is not that great if it only works for one element. So then they had to go and look for something more sophisticated. So the Bohr model has been replaced with a more sophisticated model called the quantum mechanical model.